In this lecture, I want to talk about lattice of subgroups. So that's part 3.7, I guess. Lattice of subgroups. So before I start talking about lattice of subgroups, I probably should explain what is a lattice. Before I explain what is a lattice, I should explain even more fundamental idea, what's called a partially ordered set. So let's start with this. So a partially ordered set, which everybody calls a poset, is a set, let's say X, plus a relation. And I remind you that relation is just any subset of the Cartesian product, so certain pairs. And this relation, which I will call R, and relation, so just some pairs, and the notation is that a pair AB is inside R, we denoted by A is less or equal than B. So, of course, that has nothing to do with usual less or equal of numbers, or it might have to do something, but not necessarily. And so this is this relation. So for some pairs, we say that A is less or equal than B, such that. And then there are three axioms. So they are kind of reminiscent of axioms of an equivalence relation, but they're not the same. So one of them is A is less or equal than A, which is fine. Another one is if A is less than B and B is less or equal than A, then A is equal to B. So this is dichotomy. It cannot happen that A is less or equal than B and B is less or equal than A. They should coincide, which is pretty clear. And 3 is the main important one, transitivity. A is less or equal than B, B is less or equal than C, then A is less or equal than C. So what is not necessarily true in a partially ordered set is that any pair is comparable. So it might happen that two elements are in the set, but you cannot say which one is bigger. So of course we denote by A greater or equal than B if and only if B is less or equal than A. That's just notation. A is less than B if and only if A is less or equal than B and not equal to. So all these usual rules apply. So examples are, there are lots of examples. That's a very basic structure in algebra, appearing everywhere. So you can start with something like positive integers with this usual notion of being less or equal, or like integers, or maybe real numbers. But for instance, complex numbers, there is no natural this order like that. But you can do something more strange. For instance, you can take pair of points in R, so just points of the plane, and then you can say that x1, y1 is less or equal than x2, y2, if and only if either x1 is less or equal than x2, is strictly less than x2, or x1 is equal to x2 and y1 is less or equal than y2. So one can check that it's also a partially ordered structure. Actually, any two elements are comparable here. And then there are examples which don't have this property, that any two elements are for any two elements, either one is bigger than the other or vice versa. For instance, you can take some set A, so A is a set, and then you can look at X being a set of all subsets of A. So some people denote it as a power set 2 power A, though I hate this notation completely. So all subsets of A. And then you can say that, okay, so we need this ordering, and then we say that, okay, how shall I denote them? Subsets of A, let's say so two subsets, say S1, S2, and then S1 is less or equals than S2 if and only if S1 is contained inside S2. And here, of course, it's easy to see all the axioms hold, but it's not true that any two elements are comparable. For instance, you can take as a set A, a set with two elements 1, 2, and then you have actually the following diagram. So it's very convenient to denote this poset, to draw it on the plane, and then this arrow going down means that the corresponding element is greater or equal than the previous element, actually strictly greater. So then you have empty set, which is a subset strictly less than a subset containing one element, which is strictly less than the whole set A is a subset of itself. Here we have a subset with one element, and we have the following diagram. So it's very clear that, okay, so for two elements 1 and 2, you cannot say which one is bigger, because no one contains the other. Okay, so another example is, of course, subgroups of a group. And that's fairly obvious because it's kind of the same examples. Instead of subsets of A, you say subgroups of a group. They satisfy the same properties, basically nothing to check. What else? Very interesting poset is you can take n as a set. This is X. And then you can say that, okay, A is less or equals than B if A divides B. Okay, so what will be the smallest element? So not every poset has the smallest element, but this one has. So 1 divides every number. And then over it you have all numbers which are prime, 2, 3, 5, and so on, 7. And I denote them just over because there is nothing in between. There is no number which divides 2 and not equal to 1. That's actually the definition of prime. And then you have basically numbers which are product of two primes, like 6 or like 15 or like maybe 10. And then on the next layer you have products of three numbers, for instance 30, and the diagram is actually pretty complicated. So these posets, if you try to draw them, they don't necessarily look simple. They may be very complicated. Also, it's really easy to just, associate a poset to any diagram like that. You can just take, any kind of diagram on the plane where you have a bunch of dots on every layer and some edges going from one part to another, and then you can say something like, okay, so one element is bigger than the other if it is just below. But then you need to check that this transitivity holds. For instance, if it is below, and you can go from one to another by this path, and then you need to put this transitivity condition that basically if you go from one to by some path down and then you go to another down, you can go by taking first pass and then the second, and that's obviously hold. So that's very easy to see that you can get this partial ordered sets from diagrams like this. There are lots of them, and some of them are called lattices. And for a poset to be a lattice, there is additional property which should be satisfied. Let me explain that. Okay, so a poset, let's say X with this partial order, is a lattice if for every two elements A and B, so if you take these two elements A and B, the requirement is that there exists exactly one element which is kind of immediately bigger than them. I will define it in a second. It's denoted A and then this like little thing B and another element which is called, so this one is called sometimes supremum of A and B, and this is sometimes called infimum of A and B. And this has nothing to do with calculus, supremum and infimum. So what are these elements? So there exist, every A and B in X, there exists this inf of AB in X and supremum A and B in X, such that. So what should be true? So basically the idea is that every element bigger than A and bigger than B should be bigger than supremum. So for every element C, such that C is bigger than A, greater or equal than A, C is greater or equal than B, this implies that C is greater or equal than supremum of AB. So basically, among all elements, this is the one which is the closest to AB. It is greater or equal, and every element bigger than them is greater or equal. So this is first requirement. Second requirement is, so there exists a supremum such that for every C greater or equal than A, C greater or equal than B, then it's greater or equal than supremum, and also supremum of A and B is greater or equal than A and B. So such elements should exist for every pair, and similarly for every pair A and B in X, there exists this infimum element A and B in X such that. And then there are two properties. So C is less or equal than A, C is less or equal than B, then C is less or equal than this infimum A of B, A and B. And the second one is that actually infimum is less or equal than both. So basically, the idea is that for every two elements, you can find the one kind of immediately less, one immediately bigger. And this notation is, of course, more convenient in practice. Okay, so to understand that, let's look at some examples. So examples. And of course, if you take something like X being, let's say, real numbers, then if you take A and B, this will be just maximum of two numbers. Maximum of two numbers. That's what I called supremum here, right? So that's the same as supremum AB. And infimum of AB, guess what it is? So notation is this one, and this is minimum, A and B. And of course, if you have two numbers, and then maximum of A and B can be characterized by the fact that it's greater or equal than A and B, and every number greater or equal than maximum, then both of them is greater or equal than maximum. But if your poset is not so simple, if not any two elements are comparable, then it's slightly more complicated. For instance, if you take as X subsets of A, then it's really easy to see that infimum of two sets, should be some subset inside both of them, which is contained in every subset less or equal than both of them. So, some subset of both of them C is less or equal than A, C is less or okay, and so any subset of both of them should be subset of this set, and clearly this is just intersection. And supremum is, of course, the union. Okay, so as soon as this property is satisfied, you can say that your poset is a lattice, and so these are all lattices. So this is a lattice. These are all lattices. So another example we had before, there was this interesting example. So this was first one, second one. So third one, if you take this n with this less or equal meaning divides, then it's also interesting because you can easily check that infimum of A and B is actually what's called greatest common divisor. And supremum of A and B is what's called least common multiple. So why? Again, because what is the greatest common divisor? So firstly, it should be a number less or equals than A, less or equals than B, so a divisor of both of them. Among these divisors, you want to take one which is the biggest one, so that it will be greater or equal than any other divisor. That's what's called greatest common divisor. So we will discuss this concept in detail in the first lecture about arithmetic in a few days. And supremum of A and B is the least common multiple. It's the smallest number which is divisible by both A and B. So for instance, if I take in this notation supremum of, for instance, numbers 2 and let's say 14, that's 14. That's divisible by both of them, and as the smallest such. If you take supremum of 6 and 10, you will get not 60, but just 30. And if you take infimum, so in this case greatest common divisor of say 15 and 21, you will get 3. So this is how it works. And there are lots of examples of posets which are lattices, not all of them are. I want now to talk about lattice of subgroups of a group. What is infimum there, what is supremum there, and look at some examples. Okay, so next let's look at lattice of subgroups of a group G. So definition is just you take all subgroups and partial order. So you have as a set X, you have subgroups of G, and a subgroup H1 is less or equals than H2 if and only if, and this is funny because that's how we denote subgroup. So kind of silly. Anyways, so let's look at some examples. And also I will explain notation which is typically used here. So let's start maybe with S3. So S3 is grouped with 6 elements, which you probably know very well right now. So it has this trivial subgroup. And this is what's called a minimal element in the poset. It is the smallest element. It is the element, every other element is greater or equal than that. And S3 as a subgroup of itself is the largest element and is greater or equal than any other. So then there are basically 4 subgroups. So first question you might ask is, okay, so how many layers shall we write here? And the reason, of course, there will be just one layer. So all 4 subgroups S3 has will be kind of drawn on the same layer. And the reason is very simple. Because imagine you have some subgroup G, subgroup H1, subgroup H2. So then we have this property that index of G H2, so in finite case it will be just the order of G divided by the order of H2, is a product of index of H1 in G times index of H2 in H1. And so basically if you want to understand how many kind of layers of subgroups you will have, you just need to understand what is the order of G. The order here is 6. And if the order of G is 6, then it means that you have, for any subgroup, you have that the index of the subgroup will be for any chain like that, you will have that the index of H2, 6, equals to product of two numbers. And if you imagine these groups are distinct, I mean, one of them has to be equal to 2, another has to be equal to 3. And so this is why that's very easy to understand that basically we just need, you know, two layers. So there will be two groups where, so groups containing generated by permutation 1, 2, group generated by permutation 1, 3, generated by permutation 2, 3. These are all groups of order 2, and I will just write index of a pair of groups on this corresponding edge. So that has index 2, this has index 2, this has index 2. And index of this order 2 subgroups inside S3 will be 3, 3, 3. And you have this beautiful property that you multiply along any path your indices and you get the order of the whole group. And then you have one more subgroup, which is a subgroup of order 3, which is A3, generated by 1 to 3. And it has the opposite picture, so the order is 3, the index is 2. And that's the whole structure of the poset. So basically, one element is greater or equal than another if you can go by a path from up to down to reach this element. And for these four elements, they're just incomparable. None of them is bigger than the other. So this is a lattice of subgroups of S3, and also you can easily see that it's indeed a lattice in this example. So for every two elements here, you can find an element which satisfies the axiom of infimum and the axiom of supremum. Okay, so what is in general infimum of two subgroups? So suppose you have H1, H2, and these are two subgroups inside G. And then if you take this infimum, so you want some subgroup which is contained in both, and you want the biggest one contained in both, so that any other contained in both will be contained there. And that's, of course, the intersection. So that's a very simple exercise to check that it satisfies this property of infimum. And it's slightly more messy with supremum of H1, H2, and the reason is because, okay, this should be a subgroup containing H1, containing H2, and the small as such. So we have notation for this. It's called subgroup generated by H1, H2. So you just take all elements in H1, H2, take all their products in any order with inverses, you get a subgroup. We discussed it already. But the problem is that if H1 and H2 are relatively small, it might happen that this group is huge. It can be infinite. For instance, if H1 and H2 are, I don't know, finite, Z over 2Z even. So surprisingly, though the infimum is very, very simple in this lattice, supremum is behaving badly. There is one notable exception, so maybe a fact, which is kind of interesting. So of course, naively, you want to say, okay, so let's take kind of a union, let's just multiply two groups. But product of two groups is not a subgroup. If you just start, by product I mean just multiply all elements because they don't satisfy the closeness under multiplication condition. But there is an exception. So suppose that you have N, a normal subgroup inside G, and H is any subgroup inside G. So normal, any subgroup. So then actually the set N times H, consisting of elements N times H, where N is in N and H is in H, is a subgroup of G. And the reason is, imagine you actually multiply N1 H1 and 2 H2. But you know that N is normal, so you can do this trick. You know that H1 and 2 H1 inverse is equal to N2 prime inside N. And so you can rewrite it as N1 N2 prime H1 H2, and suddenly you have another element inside N times H. And so this is indeed a subgroup. Clearly, it contains both of them because you can take identity in each. Clearly, any subgroup containing both of them will contain all products. So actually, if n is normal, so if n is normal, then it's really easy. Supremum of n and h is just n times h, where I just mean take all products. So for normal subgroups, you can do that. In general, you have some extremely badly behaving supremum. And that's, I think, is an interesting observation. So it appears many times in this group theory, especially when you do some abstract parts, but we will also see it in practice later on a lot when we work with complete groups. But right now I want to discuss it from this kind of high-end point of lattices. Okay, is there anything else I want to say here? Probably not. Okay, let me just maybe give another example. So you can take as G a group of symmetries of a square. So this group is denoted by D8, and this is group of symmetries of a square. And here the whole diagram is so much more complicated. So if you have a square, and a group of symmetries of a square has 8 elements, it's called dihedral group of order 8. And these 8 elements are, 2 symmetries with respect to diagonals, 2 symmetries with respect to these middle lines, and 4 rotations. So r by 90 degrees, r squared, r cubed, and identity. And actually, one can study the subgroup structure, and of course, as usual, on top you will have the whole group, and then it has a normal subgroup, which is just generated by this rotation, and this is a group of rotations. It has order 4, index 2. So this one has a normal subgroup of index 2, which is generated by r squared, and this one is just central symmetry. So if you do rotation by 180 degrees, that's symmetry with respect to the center. So central symmetry. And finally, this has order 2, index 4. So you see there is this nice numbers, and you multiply them to get the order of the group. So both of these groups are normal. This is actually center. And there are some other groups. For instance, if I denote this by S1, S2, S3, S4, it has a subgroup generated, for instance, by symmetry S1 of index 2, and then it has a subgroup generated by these 2 elements, and this will contain, it will be a subgroup of order 4, and this will contain S1, r squared, and it's easy to see that if you have S1 and r squared, then you actually have S2 as well. S3 and identity, order 4, and then it's index 2, and there are some other subgroups, so there is a pretty complicated diagram here. Such diagrams are usually called Fratelli diagrams. And there are very interesting questions here which are kind of immediately arising. For instance, you can try to understand, okay, given a group, can you identify a group if you know what this poset looks like? Suppose you know just, all kind of elements here, maybe all indices or something. Can you reconstruct the group? And that's a pretty complicated question in general. We are not going to address it, though there is a lot of research about it. So that's what I wanted to say about lattice of subgroups of a group, and we will see more examples of that. In the next lecture, I want to discuss how lattice of subgroups of a factor group is related to lattice of subgroups of a group. That's called comparison theorem.